Here we're going to review the u-substitution method for integration from Calculus 1. As we start Calculus 2, we need to remember several of the derivative rules that we learned in Calculus 1. These are a few of them, and they're all written in the direction that we'll use them most in Calculus 2, which is to say the antiderivative of one thing is another. And we'll be adding to this list as the semester goes along. The purpose of this video is to review the substitution technique, and so let me just do a couple of examples to remind you how this works. When we decide on a substitution, so here u equals x squared plus 4, the idea is that we make this complicated bit here much simpler. So instead of x squared plus 4 cubed, which is awful to look at, we want that just to be u cubed, and we know that we have derivative rules or antiderivative rules that will help us with that. But the catch is that when you make a substitution, you have to make it completely. And so the way we complete the substitution is by using the substitution instance to calculate an expression for the derivative of u. So in this case, the derivative of u is 2x, and then rewrite that so that it gives us a relationship between du and dx. This relationship is essential in changing this integral because the dx here has to be changed to be in terms of u, and this is the only relationship that we know between du and dx. This by itself doesn't tell us anything about du and dx. So we 100% have to use this expression somehow to change the dx into a du, and then the degree to which we use this expression changes from problem to problem. So let's see how that looks. The main thing here is to realize that as a fraction, the thing that we're integrating is the same as this expression. This doesn't look as nice, but it breaks things up in a way that we can see how to swap out equal things for equal things. So the 2x dx, as I said, that has to be used. There's 2x dx there. We're told here that it's equal to du. And so I changed this part into du. And then this piece 1 over x squared plus 4 cubed, as I said before, that's just 1 over u cubed. So that's the new integral, completely in terms of u. And so I can now find this antiderivative using my normal techniques. In this case, we want to use the power rule, so I need to first think about this integrand as being a variable to a power. Then the power rule tells us that we are just going to add 1 to the power, and of course I have my constant of integration. So minus 1/2 u to the minus 2 is my antiderivative. And then just to be polite, since the question originally involved x, then it's only polite to make sure the answer is returned in terms of x. So I will change the u in my answer back into what it's equivalent to in terms of x. And so this is the answer to the integral. And I would recommend at this point that you do check the answers, because that'll be good practice with your derivative rules. And any time you use u-substitution to find an antiderivative, that means that the chain rule must be happening to check the answer. And so when you check the answer, pay attention to whether or not you're using the chain rule and how you use it. If you decide that you're not using the chain rule when you check the answer, then that means you made an error somewhere along the way. So that's how those look. I'm going to delete this off the screen so I have room for the other ones. In this one, the relationship between u and x tells us that du is going to be 5 times dx. And here, this relationship between u and x tells us that du is going to be 3x squared plus 2 times dx. Once we've made that determination, then it's fairly easy to change these things in terms of u. One more time, I know that 5 dx is equal to du, so there's 5 dx, so that the 5 and the dx together make du. And then the expression here is left, e to the 5x plus 2. Well, 5x plus 2 is u, so that's just e to the u. So again, fairly easy antiderivative to find, and once we have the answer, putting the answer back in terms of x is polite. For the last one, again, this has been set up so that we have here 3x squared plus 2 and dx, and we know that 3x squared plus 2 times dx is du. So we get a du here, which is really just coming from this part times this part. And so that leaves us with this, and the inside of that is exactly u. And so instead of this mess to the 7th, it's just u to the 7th. Again, now it's an easy integral in terms of u. When we want to deal with a definite integral, there are two ways to do that. The simplest is probably to remember that when you have a definite integral, the values are actually x values. The 2 to 6 here is an extent, is an interval with respect to x. And so this integral is really, we could write it this way. The rationale for writing it that way is that when we decide what our integral, we decide what our substitution is going to be, then we can include in that a transformation of those numerical values. So if we use the substitution u equals 3x minus 2, then we know that that means du is 3 dx. That's part of the substitution that we're going to be doing. But we also know that when x equals 2, u will be 3 times 2 minus 2. So when you use x equals 2 in this expression, it tells you that u is 4. And when you use u equals 6 in this expression, 3 times 6 is 18, minus 2 is 16. So when we complete the substitution here, in addition to having this be 1 over u du, which is what's going to happen to the integrand part, but also we can change the limits of integration to be in terms of u. And so instead of having the integral go from a value of 2 for x to a value of 6 for x, we're going to have it go from 4 for u to 16 for u. And so when we evaluate this integral, this will be natural log of u from 4 to 16, and so we'll have natural log of 16 minus natural log of 4 as a final answer. So if we look at the steps written out, we see that we see that this is what we end up with. Notice that there are some rules of logarithms that would allow you to simplify that one step further, and I'll leave that for you to do. So here are some practice problems with using definite integrals, and I'll just do each one, and then you can skip between them. So there are 3 of them here. So first of all, we know that if u equals x squared, then du is 2x dx. And we can see in our integrand that we have the 2x dx here. So if I were writing out all the steps, I would write this out. First, just rewriting the integral, then realizing this is 1 over u cubed times du. But now I'm going to remind myself that the values here are x values in the original problem. The original problem said 0 to 4 in terms of x. And so when I get over to the new integral in terms of u, I need to transform those numbers as well. So I go back to my substitution and I say, well, when x is 0, u is 4. So and when x is 4, u is going to be 4 squared plus 4, which is 20. And so we saw before that the antiderivative here looks like that. Now we're evaluating from 4 to 20, and we can continue to do that. Here's this integral again. Remember, this meant du is 2 dx, and so when I write down my definite integral, I remind myself that this is in terms of x, and again I would rewrite this so that it's very obvious. Here's my du, here's e to the u, well, I guess I could, and I need to transform my limits of integration, and so I go back, and when x is -5, u is going to be twice -5 plus 1, so that's -9, and when when x is 0, u is going to be 1, and so I end up with the antiderivative being e to the u, and I want to evaluate that from -9 to 1. Finally, oh, this has got a typo in it. Does it? Oh, no, it's okay. It's just not the same as the one before. Yeah, so du is 3x squared plus 3 dx. And so I've got my x cubed plus 3x plus 7, or sorry, plus 1 to the 7th times 3x squared plus 3 dx, and that's x equals 0 to x equals 1, and all I'm doing is rearranging the terms. I didn't really do anything. I just put this term over with that term so that I can see it. Now I see this is du, and this is u to the 7th. But I have to transform the limits of integration as well. When when x equals 0, then 0 plus 0 plus 1 gives us u equals 1. And when x equals 1 here, then 1 plus 3 plus 1 is 5. So I end up with 1/8 u to the 8th evaluated from 1 to 5. So that's the basic idea. The real challenge, of course, is when you're not told what substitution to make and when the problems haven't been sort of geared to work out well in the first place. So one example of that is here, where you have x squared plus 1 to the 5th times x dx. So we want to use u in for x squared plus 1 because that would give us u to the 5th here. But things don't quite match up when we do that, because when we have u equals x squared plus 1, then du is 2x dx, and I don't have 2x dx in the problem. When we have, so what I do instead is take the 2x dx and then ask myself, what do I want? I have 2x dx, I would like x dx. And so if I know what 2x dx is, then I can figure out what x dx is, because that's just a matter of multiplying by a half. So by introducing a half into the problem, now I have 2x dx. You can see these two things are equal because a half times 2 is 1. So x dx is really the same as 1/2 times 2x dx. And now this 1/2 sitting out here is just waiting around for the rest of the problem to happen. So u to the 5th du is an easy antiderivative. And I end up with 1/12 x squared plus 1 to the 6th. And again, checking the answer is really important. When you check this answer, you will find yourself using the chain rule in a way that that tells you that you were right. You'll use the chain rule and your inside function will be x squared plus 1, and that's because your original substitution was u equals x squared plus 1. So here's 3 more examples of this that we can do. From the given u here, I know that du is 2x dx, but I want my original integral looks like this. It's 1 over x squared plus 4 squared times x dx. And so I don't want 2x dx, I want x dx. So by multiplying both sides by a half, I now have an expression on the right for x dx is 1/2 du. And that 1/2, so I can go ahead and say 1 over u squared times 1/2 du. And like we saw before, that 1/2 actually comes outside of the integrand. And so now that's a fairly easy problem. And again, we'd want to put our x's back in at the end. Here's another example of it. Here du is 5 dx. And so I don't really have a 5 dx sitting anywhere. I have just dx. And so I ask myself, if du is 5 dx, then what's dx? Well, multiply both sides by 1/5, and you have an expression. That dx is 1/5 du. And again, the 1/5 can come outside of the integral. And now it's a fairly easy problem to finish. Here's the last one from this substitution. I have du equals 3x squared plus 3 dx. In the original problem, I have x cubed plus 3x plus 1 to the 1/2 times x squared plus 1 dx. And so I have this thing in my problem, and this is what I know. So it's not quite as obvious as some of the other ones, but if you notice, in this expression, if we were to divide both sides by 3, I'll have 1/3 du equals x squared plus 1 dx, which is exactly what I want. So in this integral, I'll have u to the 1/2 power times 1/3 du. Once again, 1/3 comes out in front, so it gets out of our way, and I end up with just the integral of u to the 1/2.